Hi guys, how are you? Just give it another minute and then I can get started. How you guys doing today? Okay, so we left off last time on chapter 1.5. We were talking about implicit equations. So implicit equations are equations that don't have a parameter in them. Remember, our old equations had some kind of a point. They had a parameter, like t, we called it, and they had some kind of vector, okay? The point and the vector helped us to orient to that particular, whatever, it was a line or a plane, okay? If it's a line, I need one point and one vector. If it's a plane, I need two vectors and one point in order to orient for it. Okay, now, when we're creating an implicit equation, okay, we're typically talking about vectors that are perpendicular, either to the line or perpendicular to the plane, okay? And so we were talking about how we are going to create our equation, okay? That's an implicit equation for our plane. Now, when we talked about our plane equation, we said we have ax plus by plus cz equals d. It can also be written as a times x minus x naught, b y minus y naught, c times z minus z naught, where x naught, y naught, and z naught are points on the plane, or like their coordinates, x, y, and z coordinates for a particular point on the plane. Okay, the coefficient a, b, and c, the coefficients for our x, y, and z, are the vector. They make up the components for the vector that's normal to this plane, okay? So now, when we did our last example, okay, for 1.5, we did 3 points. We want to write a standard equation, which is implicit, for a plane containing these 3 points. So I needed two vectors, right, my displacement vectors using these 3 points. To create the implicit equation, I take the cross product of those two vectors. That cross product is going to give me a vector that's normal, orthogonal, perpendicular to that plane, okay? So the two vectors are on the plane, and now I'm creating that vector that's normal. Excuse me, that's normal to that plane. Okay, so now I have a particular point on the plane, which we said was 0, 3, 0. We chose that one. That was our initial point. I said 0, 3, 0, because that is my point on the plane. And then actually it didn't even matter. It didn't have to be the initial point, could be any. And I used that normal vector to create my implicit equation. Okay, so that was example 3. Now, I'm moving on to example 4. Okay, we're going to keep talking about our implicit equations for lines and planes. Okay, we're gonna work through some more examples in class. And then I've got classwork for 1.5 that I'll work through and keep going. And in the meantime, you guys can ask me questions about classwork or homework or what have you for 1.3 and 1.4. Don't forget, we have a quiz starting today. Starts at noon today, goes to noon. It's available from noon today to noon tomorrow. And you have 30 minutes to take it. And that'll be on chapters 1.3 and 1.4 only. So I'm collecting those classwork, 1.3, 1.4, and the homework for 1.3 and 1.4. That'll be, the classwork and the homework are due at midnight, and the quiz, you have a 24-hour window within which to take it. Okay, let's go ahead and get started. So we're on lecture examples for 1.5, and we're looking at example number 4. Okay, so we've got a plane that's perpendicular to this vector right here. And it goes through this point, and we want to say what equation, what's the implicit equation that will describe this plane. Okay, so let's I always like to kind of draw a picture just so I can think about it in my mind. You don't have to. You're typically not graded on your pictures, but it can help you kind of think about what's going on. So here's my point, which is 1, minus 1, 3. Okay, and then on this plane, I have the vector that's perpendicular to that. So this is 2, 1, minus 1. Okay, now remember, our implicit equation for a plane was basically like I had my normal vector, okay, which is going to be, so we'll call this n. That's going to be a, b, and c are the components for that vector. Okay, now what I can do is I can say, I can dot product that with my x, y, and z, my generic x, y, and z, and then dot product that with my point to get the implicit equation, or I can plug it into my implicit equation generic equation. We'll do both methods so that you can see. So here's, you're going to get the same answer either way, but we'll do the dot product method first. Okay, where I'm going to take my normal vector 2, 1, minus 1, and I'm going to dot it with x, y, and z. That's my generic, any generic point on that plane. And then that's equal to my normal vector dotted with the point 1, minus 1, 3. And now I'm just going to do my dot products. Remember the dot product, I multiply corresponding components and I add them up. So 2 times x plus 1 times y plus a minus 1 times z equals, let's do this, so 2 times 1 plus 1 times minus 1 plus 1 minus 1 times 3. So this is 2 plus a minus 1 minus the 3. So minus 4 plus 2 is minus 2. 2x. Did I do that right? Is this, did I do that one right? Yes, minus 1 there. Okay, so 2x plus y minus z equals minus 2. You guys should check my math as I'm doing this too, just to make sure that I'm doing it correctly. Okay, so 2 minus 1 minus 3. Good. Okay, so let's do the other. We're going to do the generic equation. Just so you can see both methods, and you can choose which method you like better, and then do that one. All right, it's going to be a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. Okay, so a, b, and c are our normal vector. X naught, y naught, z naught is the point. So I'm going to plug things in. So it's going to be 2 x minus 1 plus 1, put the 1 here, y minus a minus 1 plus c, which is minus 1, times z minus 3 equals 0. So let's multiply it out. So 2x minus 2 plus 1y plus 1 minus z plus 3 equals 0. All I did was distribute these terms, and I'm going to combine. So 2x plus y minus z. So this is 4 minus 2 plus 2 equals 0, and which I can bring the, sorry, I can bring that 2 over to the other side to make it look like this one. X plus y minus z equals minus 2. Okay. Same equation. You should get the same equation when you do this. They're just two different methods. Whichever one you feel more comfortable with is totally fine. Okay. Okay, so we've come up with an equation for the plane. For the plane. It's called the implicit equation because it doesn't have a parameter, okay? And it just relies on the normal vector to that plane. Okay. All right, I'm going to turn the page. All right, example 5. Show that the two planes are perpendicular to each other. Okay, so given. So we've got P1 is x plus y minus 3z equals 2. P2, 4x minus y plus z equals 1. Okay, good. All right, so perpendicular to each other. So the two planes are perpendicular. So I'm going to just kind of come up with a rough sketch. What does that mean if my two planes are perpendicular? So I've got plane 1. Start out like this. So plane 1. And then plane 2, let's say it looks like okay, so I've got these two planes, and like I said, you're not being judged on the math here, but so we're saying that these two are perpendicular to each other. Okay, that's what this means. So now what I'm going to do is I'm going to think of the pieces that I have on here. So let's start extracting the information that we have. So for plane 1, I've got my normal vector for plane 1. I'll call it N1, which I'm just going to extract. The coefficients for x, y, and z are the normal vector, 1, 1, minus 3. my normal vector for plane 2, extracting the coefficients 4, -1, 1. Okay, now, if the two planes are perpendicular, right, that must mean that I've got a normal vector. Let's draw it like this. I've got a normal vector coming off of here. So let's say this is normal 1. This is going to be normal to plane 1. And then I'll have a normal vector coming off of plane 2. That's normal 2, right? So if the two planes are perpendicular to each other, then that means that the two normal vectors must be perpendicular. Let me write that. If plane 1 is perpendicular to plane 2, then normal 1 must be perpendicular to normal 2. Because plane 1, plane 2, right? So normal 1, normal 2, they must have the same angle relationship. Okay. All right. Which means then, these are vectors, which means then that n1 dot product with n2 must be equal to 0. If that's true, then I can show that these two planes are perpendicular. So let's go ahead and try that. So my n1, 1, 1, minus 3, dot product with 4, -1, 1. Let's see what we get. So corresponding components, 1 times 4 plus 1 times -1 plus -3 times 1. So this is a 4, -1, -3. So 4 minus 4 equals 0. Check. Okay, so the two planes are perpendicular to each other because the two normals are perpendicular to each other. 90 degrees, 90 degrees. If they're perpendicular to each other, then the planes must be also. Okay. These are some things that you can do now that you know what the implicit equation is and all the pieces for it. Give you guys a chance to finish writing that, and then we'll talk about example 6. Example 6 is actually like example 4. So 6 is a lot like example 4, where I've got has the point, and this is our normal vector here. So we can do one of two things. You know, we can do the dot product method. I'll do the dot product method. It's fairly straightforward. So I'm going to go n dot x equals n dot our point. Okay. So I'm going to plug that in. So this is 5 minus 3, 7 dot x, y, z equals 5 minus 3, 7 dot 3, 1, minus 2. Okay. So I'm going to get 5x minus 3y plus 7z equals, so it's corresponding pieces, 5 times 3 plus a minus 3 times 1 plus 7 times a minus 2. So this is 15 minus 3 minus 21. So minus 3 minus 21 is minus 24. So 15 minus 24, okay, those are 15 minus 24 off the top of my head. Let's make sure I'm doing that right. So 15 minus 24 is going to be equal to minus 9. 5x minus 3y plus 7z equals minus 9. You guys should check my math on this too. Oh, I see my problem here. This, I did 7 times 3, but it's 7 times 2. I was wondering why that was off. Okay, so I made a typo. This is a minus 14 here. So that's why this is here. Okay, so minus 3, minus 14, that's minus 17. 15 minus 17 is minus 2. So here's our equation. Good, it's good to check the math. Okay. I'm going to scroll up. So plane P is given by this equation. We want to find a non-zero normal vector to the plane and determine a point on the plane. So normal vector to the plane means I'm just going to extract out the coefficients for my x, y, and z. That gives you my normal. So my normal equals 6 minus 5, 3. See these? 6 minus 5, 3. That's the normal vector. Okay. To determine a point on the plane, your best bet for determining a point on the plane is looking at your intercepts. my X, Y, or Z intercept. We'll do all three just so you can see what they look like. Okay, so if I do a Z intercept, that means where does it cross the Z axis? So what I do is I set X equal to 0, Y equal to 0, and I solve for Z on my equation here, right? So this becomes 6 times 0 minus 5 times 0 plus 3Z equals 7. I brought the 7 over to the other side to make it easier. Now I divide both sides by 3 and I get Z equals 7 thirds. So my Z intercept is 0, 0, 7 thirds. That's a point on the plane. Not too bad. My X-intercept, it's the same process, except we set Y and Z equal to 0 and they solve for X. Y equals 0, Z equals 0, solve for X. Okay, this is just the process on how we're going to do it. So 6 times X minus 5 times 0 plus 3 times 0 equals 7. Okay, that means X is going to equal 7 divided by 6. So our point is going to be 7 divided by 6, 0, 0. They're just asking for 1 point, but I'm showing you how you can get an intercept, right? And you can choose, do you want an X, a Y, or a Z intercept? But at least you'll know how to do it. A Y-intercept, let's do that one lastly. So in this case, I set X equal to 0, Z equal to 0, and I solve for Y. Okay. So I'm going to say 6 times 0 minus 5 times Y plus 3 times 0 equals 7. Okay, that means my Y is going to equal minus 7/5. So the point on the plane is 0 minus 7/5, 0. And so that's how we do that. Okay. And that's it for chapter 1.5. Okay. These are all of our examples. And now what I was thinking I would do is I would work through the classwork for 1.5. I've got part 1 and part 2 here, and I'll just start working through. So, so you guys can see what these things look like. Okay. You guys all have this before I move it. I'll scan it in later today and then put it up on our website. All right, so I'm looking at my classwork. Now, this is going to be part 1. I'm pretty sure that's part 1. Okay, so I'm just going to start working it through. You guys are welcome to work it through. You can stop me and ask questions. I'll open up my chat window here if you have any questions you want to put into the chat. I'm still trying to figure out how to do breakout groups if we want to do something like that, where I can group you guys and you can talk together. But I think, you know, at the moment, we're kind of working independently on our classwork, but I will work on it now while you guys are hopefully working on it too, and then we can check. You guys are also free to ask me questions on the homework too, if you want to do that. I'm totally good with answering questions on the homework. We can go back over some of the other classwork too. I just wanted to work through the classwork for 1.5 a little bit. Everybody see how I did this here? We were given a vector parallel to the line. Right, so if I'm given this vector here, I need to find, for the implicit equation, I have to get a normal vector for that. So I need to take my vector that's parallel to the line, and I switch the x and the y, and I negate the new y. Right, so 4, this becomes 4 minus 3. This becomes -1, -1, or I can work in all positives, which is the same thing as 1, 1. All it means is that my normal vector goes in the other direction. This one's kind of a trick. You have to think through number 2 a little bit. So we want a vector equation for a line that contains this point, and the line is perpendicular to this plane. So if I'm given the plane equation, x plus 2y minus 5z plus 7 equals 0, and I just kind of draw it out. I've got my normal to the plane. My normal to the plane is just the coefficient. My vector is coefficient of the x, y, and z components. So 1, 2, minus 5 make up the vector components for the normal to that plane. Now what I want is the vector equation to describe this line right there, the line that is going to contain this. So remember, this is the plane. It's perpendicular to that normal, but I want the line that contains that vector. It's parallel to that, the vector is parallel to that line. So my vector equation format is x bar equals x naught bar plus t times v, right? V is actually my normal vector, right? It's normal to the plane, but I want to make that as the vector parallel to my line. So I'm going to go, this is the point they told me to use, plus t times, this is the vector. So I help to kind of draw out a picture on that one, just to think about it. All right, this one, find a second point on the line which contains the point 1, 1, 1, which is parallel to the line given by this. So I'm just going to draw this out so I can visualize it. So I'm given a line equation, which is x bar equals t times 2 minus 1, 2. That's this line. That's this one here. Now I'm told that my other line equation, my other line is parallel to that one. If they're parallel, it means that the vectors on those lines are parallel to each other. They're just scalar multiples. This other line right here contains the point 1, 1, 1. This is kind of like y equals mx plus b. This one doesn't, the y-intercept is 0, this y-intercept is 1, 1, 1. You can kind of think about it that way, right? Equivalent. This right here, so my new equation for this parallel line is 1, 1, 1 plus, I use a different parameter, s times 2 minus 1, 2, right? This is the same vector. So now finding a second point, the first point is 1, 1, 1. Finding a second point means I'm going to choose some s value. I can choose whatever value I want, right? I can choose, I don't want to choose 0 because that would give me the same point that they just gave me. So I'll just make it easy for myself. I'll choose s equals 1. I mean, I just chose that randomly. So I'm going to go 1, 1, 1 plus 1 times my vector 2 minus 1, 2. That's just my format for my line equation. So I'm going to combine parts. If you had chosen a different value for s, you'd get a different point, but it would be equally correct. A lot of these are review, but that kind of helps us to kind of think about what's going on. So we need a line segment from the point here to the origin. Okay, so on this one, question 4, doing a line segment from the point -1, 0, 7 to the point 0, 0, 0. That's the origin. I need a displacement vector. They want lines parameterization. So this is going to be our vector equation. So remember, our displacement vector is terminal minus initial. So terminal, initial, I subtract them. I'm going to get 1, 0, minus 7. That's my displacement vector. Now my equation, my vector equation for the line is x bar equals x naught plus t times b. My x naught, that's my initial point. So that's -1, 0, 7. My vector is the one I just calculated. To make this a line segment, I have to restrict my parameter value to be between 0 and 1. So both of these here I need in order to define my line segment. Okay, so this one I'm just going to plug right in. This one here, I'm giving it in terms of standard basis vectors, but I'm just going to strip it out and make it into vector components. So I'm going to use that. I'm going to leave this here. I'm going to leave things in terms of radicals instead of trying to come up with a decimal. This one I'm going to work on the other page where I have more room. So I've got a point and I have two vectors, and I need to come up with the implicit equation for my plane, which means I need to do a cross product of these two vectors. So my normal will be V1 cross V2. And then I need to put that into my plane equation. So I'm going to work on the other page here. 0 minus 3. Is equal to and the point is equal to minus 3, 1, 0. Let me just draw a picture just so I can visualize. Okay, so I just found my normal vector. I'm going to use the generic equation because I've got a point that I'm dealing with here. Okay, I plugged in my point. This is a minus 3, so it's minus and minus becomes a positive. This is minus 1, minus 0. So I'm going to distribute now my terms. And I can actually just divide by a negative to make that all positive. This was question 6. This is all being recorded too, so you guys can pause the recording and take a look at it. Right. Find a vector equation which contains the point parallel to the line given by this. The line, so which we just probably want to have a vector equation of the line, perhaps. Okay, so let's talk about this one. So I've got a line. This one has 7 as a point. This has our vector. Okay, so we want to have another line that's parallel to this one, and it contains this point. I think we did one like this already. I'm going to use a different parameter, S times. I had to read the question, see what they're asking me. They just wanted to come up with another vector equation. These two lines are parallel to each other, so which means they have the same vector. They're scalar multiples of each other. Use a different parameter than the one given, and the point is different because it's different reference point for our line. Here we have two parallel planes. There's the equation for the plane. So I'm going to have a plane. 2x plus y minus 3z plus 7 equals 0. And I have another plane. Okay, so this one here I'm going to talk about. So my normal vector on plane 1 is equal to 2, 1, minus 3. So let's say this is my normal vector for, this is 1. This is my normal vector for 1. If these planes are parallel, then their normal vectors are going to be parallel too. So then I'm going to say this one, my normal vector for this plane has to be equal to that one. But this new plane contains a different point. Okay, so I'm going to come up with a different, I want a plane with the same normal vector, but with a different reference point. Okay, so we can do either generic equation where you plunk things in, or I can do the dot product. So I'll do dot product. So this is n dot x equals n dot. Dot. So the equations are really similar. Look at this one. 2x plus y minus 3z equals minus 7. That's this one. 2x plus y minus 3z equals minus 9. The planes are the same. Have this parallel normal vectors, but they have this one contains this point, this one contains that point. That's how you tell the difference between them. So give an equation of the form ax plus 5y plus cz for a plane that contains this point and is parallel to that one. Okay. Now we have, again, two planes that are parallel. Plane 1, which is ax plus y plus cz plus d equals 0. Parallel to this one. So that means that the two normal vectors, so this is it's going to be, let's call it minus 3, but this has a 5 and this has a 1, so I have to multiply n1 times 5. So n1, it says scalar multiple. Parallel means that they're scalar multiples, but see how there's a 5 here and there's a 1 there, so I have to multiply this vector here, my normal vector from here, by 5 in order to get the scale. So the normal vector is going to be 10, 5 minus 15. I'll do the generic equation method. I'll fill in the blanks. A, B, and C are my normal vectors. X naught, Y naught, Z naught is the point. And I get to distribute. I can leave it like this, but I'm going to distribute.
Miss Wilson, can you do number 2 on 1.3 part 2 when you get a chance?
1 point, is that a classwork or is that homework?
Classwork.
Classwork, okay, sure. Let me just finish this up and then we'll,
Thank you.
yeah. Where's the shape? Okay, and I just realized that the classwork for 1.5, the part 2 is the same question that we just did for question 6 on here. So I think this wraps up 1.5 classwork. So when you guys pass it in, don't worry about passing in this one. This is the same question that we just did, I think, on question 6. They look the same anyway, I think. Yeah, they're the same. So don't sweat it. I'll take this one off. This I think is part 2, so it's a duplicate. Don't worry about that one. All right. Tommy, can you remind me which one you asked about?
It was number 2 and 3 on classwork 1.2. I
One
mean
point-
1.3.
1.3. Okay. All right. Let me find it. Give me just a second.
Thank you.
Yeah, no problem. So here's 1.3. Was it this one? Or was it this one?
Yeah, it's that one.
This one right here? Okay.
No, the other one. I'm sorry.
The first one?
Yeah.
Okay. Alrighty. All right, so let's talk about it. All right, so this is classwork 1.3. It starts off with this at the top. And then question 3. The double bars is another way of saying magnitude. Okay, so different books use different notations. So I'm trying to use a lot of different notations so you can get a feeling for how the different books use different things. So we're going to let the magnitude equal to 3. So we want to know which of the following vectors is a possible value of V. So I'm looking at what are my magnitudes here. So I check the magnitude of this one. Actually, you know what? I think this probably could be 2 because this is 9 times 3. So this is 3 radical 3. So this possibly could be 2 because it's a scalar times that. So so if I take the magnitude of A, this is 1 squared plus 4 squared plus 0 squared. That gives me radical 17. So that doesn't have a magnitude of 3. It's not even like, you know, closely associated with it. I can't even do a scalar on that one. If I take the magnitude of this one, right, I get radical 5. If I take the magnitude of this one, I get 9 plus, you know, radical 27, which is 3 times the radical 3. That's similar. I could probably, this could be like a scalar multiple of V. So possibly, I'll write possibly here. Like if this was my scalar multiple of V, so I could go radical 3 times V, that would give me a magnitude of, let's see, no, this has a magnitude of 3 radical 3. So I'd have to divide V by radical 3. So I'll put possibly, but more likely, this one right here, look. I take the magnitude here, I'm gonna get 2 squared plus minus 2 squared plus 1 squared. I'm gonna get that magnitude is equal to 3. So this one has a value, a magnitude value equal to 3.
Okay, I think I did it right. I forgot to simplify the last one, so I got confused. Because
yeah.
I got radical 9, but I just forgot to simplify it to 3.
That'll do it.
So,
yeah. Yeah.
Yeah.
I remember. And then part 3 says if U has this for components, so it's a 4-dimensional vector. So all the math scales up, even though we have a hard time drawing it. 1k minus 2 comma 5, and it has a magnitude equal to 6. So what are possible values of k? So what I'm going to do is, I know my magnitude is, I take each component, I square it, I sum it, take the square root. So I'm going to say 1 squared plus k squared, right? I don't know what k is, plus a minus 2 squared. Watch your negatives, plus 5 squared. sum it up, square root it, equals to 6. I was told that the magnitude equals 6, right? And so now I combine all the numbers and I have k squared plus 30 equals 6. Now I want to get this, I want to solve for k, so I got to get it outside the radical. So I square both sides of my equation. That gets rid of my radical here. 6 squared is 36. I subtract 30 from both sides. I get k squared equals 6. I take the square root because I want k, not k squared. So k equals, and remember, it's plus or minus. When I take the square root, it's plus or minus, because if I square a positive radical 6, I get 6. If I square a negative radical 6, I get 6. So that's why it's plus or minus. So those are possible values of k.
Okay. Let's see. Thank you.
You're welcome.
I think that was all the questions I had.
Okay.
More
All right.
later.
Great, you guys. If you guys don't have any other,
I'm sorry, I did have another question.
go for it. What's up?
I think this one was about the homework.
Okay.
It was number 9. It just confused me about like how you would go about finding A on number 9.
Okay, let me get up my solution here and take a look. So, 8 and 9. Okay, so it's a triangle with the vertices and has a right angle at 0, 0, A. What is A going to be? All right, so I did it like this. I'll do it out from the start. So this is question number 9 from our homework. So we have triangle with vertices. Let's see, 1, 2, 0, 2, minus 3, 0, and 0, 0, A. Right, this is what we're given. And I called this B and I called this C just so I could kind of keep track. And it has a right angle at 0, 0, A. And we want to know what is A. Right, so I kind of looked at it like I've got this triangle kind of looks like this. Right, so this is 0, 0, A. This one I said was 2, minus 3, 0, and this one was 1, 2, 0. Like if I plotted it out, look kind of like that. And this, I'm not drawing it very well. So now I need to figure out what that is. So I'm going to come up with displacement vectors from here to here, and then here to here, right? So if I do displacement vectors, the reason I want to do that is because if I take the dot product of displacement vectors and they're perpendicular to each other, then the dot products can be 0. So if I calculate a displacement vector, right, so this is going to be terminal minus initial, 2, minus 3, 0, minus 0, 0, A. And then the other ones, this is my first displacement vector. I'll call that one AC. And then we'll call AB. Say we're going to go this one, terminal, minus initial. That's an A, right? So now what's going to happen is AC looks like this. 2 minus 0, minus 3 minus 0, 0 minus A. So there's a minus A right there. And then AB says 1 minus 0, 2 minus 0, 0 minus A. Right, so I've got my two displacement vectors. And now if AC is perpendicular to AB, their dot product is equal to 0, right? So I'm going to take their dot product. So I'm going to go 2, 0, minus A, dot, 1, 2, minus A. And I'm going to set that equal to 0. And I'm going to solve for A, basically, right? So it's going to go like this. 2 plus 0 plus A times minus A times minus A is just A squared. That's equal to 0. Did I do something wrong? There should be, oh, there should be 3. Yeah, I wrote it down wrong. So this is a minus 3 minus 0 is a minus 3. I knew I wrote that down wrong. Minus 3. So minus 3 times positive 2 is minus 6. There, good. All right, so now I'm going to get, this is going to be minus 4 plus a squared equals 0, right? And then you get minus 4 equals a minus a squared. I can divide by minus 1, so I'm going to get 4 equals a squared. I take the square root of both sides. So positive or negative 2 equals a. Okay, so either one of those will work. Positive or negative 2 will give me a dot product equal to 0.
Okay. Yeah, I was just confused about it.
Yeah, right. It takes a little bit of thinking, and I always have to draw these out so I can like conceptualize what I'm trying to do. And in the process of drawing it out, my brain, like on the back burner, starts to think about like, well, what tool do I have that I can use that'll show me that things are perpendicular? Perpendicular is like important, right? So we've got
Yeah.
like the dot product will tell us things are perpendicular. So if I've got these, points, right? How can I use the dot product on them? Well, I can figure out a vector, right? So this is going to be AC, and this is going to be AB. So I'm going to take the dot product of those two vectors and set it equal to 0 because I'm telling everybody these two are perpendicular. And then I have to find out that unknown variable, what value of that unknown variable is going to make that perpendicular, make that dot product equal to 0.
Okay.
Yeah.
Yeah, I got it.
It's a lot. It's a lot of things you kind of bring together,
Yeah, that's something that I'm just looking at it right now.
Yeah. It takes a minute to let it sink in and think about. Even I have to still think about it.
All right. Thank you.
You're welcome.
And that was number 9. Yeah. Okay.
Yep.
And okay, I think that I'm good.
Okay, good. Anybody else have any other questions? Otherwise, I'll let you guys go. And don't forget, things are due at midnight tonight, and your quiz opens up today at noon, and you have until noon tomorrow. If you have trouble accessing it or trouble uploading it, send me an email and we'll figure it out. Okay. Otherwise, have a great weekend, and I'll see you guys on Monday.
All right. Thanks.
Bye, guys.